In this section of the course, we'll learn about our first compound data type. A compound type is a type that's made up of other types. First, we'll learn about arrays, what they are and why we use them. We'll go over the syntax for declaring and initializing arrays, and we'll learn how to access the individual elements of an array. Then we'll talk about multi-dimensional arrays. These can be two-dimensional or three-dimensional arrays, or they can be as many dimensions as you need. They can be very useful for modeling grids, boards, and much more complex data types. Then we'll learn about vectors. Vectors are better than arrays in so many ways, and we'll discuss their advantages. In fact, in modern C++, we rarely use raw arrays. Instead, we use vectors. So why cover arrays at all? I think it's important to understand arrays since there's so much legacy C++ code out there, and conceptually they're easy to understand and they'll add to your overall knowledge of C++. Okay, so let's get started learning about our first compound data type, arrays. In this video, we'll learn about arrays and their characteristics. We'll also see the typical use case for an array. An array is a compound data type or a structured data type. This means that it's a data type that's made up of other data types. For example, a collection of test scores where each test score is an integer is considered a compound data type made up of integers. We say that this is an array of integers. It's important to understand that all elements of an array must be of the same type, and each element can be accessed directly. We'll see some other array characteristics shortly, but first let's see why we use arrays and why they're so useful. Suppose we need to model my test scores in a class. That's pretty easy. We've already seen how to use variables, and this would be a perfect use of variables. So suppose I have 3 test scores that I need to track, and they're all graded as integers out of 100. I can simply declare 3 variables as integers, give them meaningful names, initialize them to 0 or to whatever values I wish. But what if I need to model more than just a few test scores? Suppose I'm a school administrator and I need to model the test scores for 100 students so that I could do some statistics on them. Modeling each one of them as its own variable with its own name can quickly get out of control. Now I have to keep track of 100 variable names. You could still do it, but it becomes tedious and error prone. What if I had 10,000 test scores to model? You get the idea. This is a typical use case for an array, and that's when they're really useful. Arrays allow you to tell the compiler to give you a collection of as many elements as you want and give the entire collection a single name. So you no longer have to name each individual element. Let's go over some of the characteristics or properties of arrays. Arrays are fixed in size. Once you create an array of a specific size, the size cannot change. So if you create an array of 100 test scores and then you need space for more than that, you'd have to go back to your source code, change the max size, and recompile. The size of the array is fixed. Arrays will not grow or shrink on their own while the program is running. As mentioned earlier, all the elements of an array must be of the same type. So we can have arrays of integers, arrays of doubles, arrays of persons, arrays of accounts, and so forth. Arrays are stored contiguously in memory. So if you tell the compiler that you need an array of 100 integers, the compiler will generate code that allocates exactly 100 integers that are contiguous in memory. That means that the memory will be allocated as one chunk. Array elements are individually accessible, so I can access any test score that I wish. You can do that using the position or index of that array element. So I can tell the compiler to give me the second element in the array or the 1500th element in the array. Be aware that array indexes start at 0. This means that the first element in an array is at position 0, not at position 1. And the last element is at position size -1. You can see an example in the figure on the right. Here we have an array of 10 test scores. The array is named test scores and it's indexed from 0 to 9. Many programming languages have compound data types like arrays, and the majority of them start their array indexes at 0. I know that most of us start counting at 1. With arrays, you must start at 0. This is a common cause of errors in programs, especially with beginning programmers. It's also important to understand that C++ arrays are not bounds checked. That means that there's no check to make sure that when you access an individual array element that it's between 0 and size -1. It's the programmer's responsibility to be sure that you don't go over bounds. If you go over bounds, your program may have strange behavior and you could even crash. Finally, in a few sections, we'll talk about iteration or looping. As you can imagine, looping is used all the time with arrays since we often need to loop through the arrays and process every element. Just like variables always initialize the arrays or they'll contain unknown values. Arrays are extremely efficient in C++ since they are bare bones raw arrays. Later in this section, we'll talk about C++ vectors, which are super powerful, dynamic, and safer to use than arrays. In the next video, we'll see how to declare arrays. In this video, we'll look at the syntax for declaring and initializing arrays. The syntax for an array declaration is very simple. First, we write the type of each element in the array. This is followed by the name of the array variable. Then we provide square brackets, which is the array indexing operator, and in the square brackets we provide the size that we want the array to be. Remember, this size is fixed, so the compiler must know the size of whatever's in the square brackets at compile time. So this can be a constant literal, it can be a declared constant, or a constant expression. In the first example, we're declaring an array named test scores of 5 integers. The second example declares an array named high scores per level of 10 integers. And the third example declares an array named high temperatures of 365 doubles. Notice that days and years are declared constant so the compiler knows its value. Also note that in all three cases, the arrays have not been initialized. This means that the contents of the array elements could be anything. Best practice is to always initialize arrays when you declare them. Let's see how we can do that. We can also initialize arrays when we declare them, and it's good practice to do so. The syntax is similar to when we initialize primitive variables. We include an initialization list after the declaration. In this list, we can provide as many initializers as we like, separated by commas. In the first example, test scores is initialized to 100, 95, 99, 97, and 88. The initialization works as you would expect. The test scores array element at index 0 is initialized to 100, the element at index 1 to 95, and so on. In the second example, you see that we declared an array named high scores per level of 10 integers, but we only provided 2 values in the initializer list, 3 and 5. In this case, the first 2 elements of the array are initialized to 3 and 5 respectively, and the remaining 8 array elements will be initialized to 0. In the third example, all of the elements of the array high temperatures are initialized to 0. This is a very handy initializer that's used very often. The final example is a little bit different. In this case, I didn't provide any number for the size of the array inside the square brackets. Instead, I'm letting the compiler determine the size of the array based on the number of elements in the initializer list. This form is also often seen. In this case, another array will be of size 5 integers, and they'll each be initialized from 1 to 5. As you can see, the syntax for declaring and initializing arrays is very straightforward. In the next video, we'll look at the syntax for accessing individual array elements. In this video, we'll look at the syntax for accessing individual array elements. The syntax is probably very much like what you expected. We use the name of the array followed by square brackets with the index of the array element that we want inside the square brackets. This is called array subscripting. For example, test score sub 1 refers to the element at index 1 in the test scores array. In the code example at the bottom, you can see that we've declared the test scores array of 5 integers and initialized those integers. Then we have 5 output statements that each displays one of those array elements. Remember that array subscripting or indexing starts at 0, so the first element of an array is at index 0. We use the same syntax for storing values in array elements. In this example, we're getting input from the user via the console and updating the individual array elements from index 0 to 4. We could then display them as we did in the previous slide. We'll talk about assignment statements in an upcoming section, but here you can see that I'm assigning 90 to the first element of the test scores array. Notice that the syntax is the same. That pretty much covers the basics of arrays, but you might be wondering how all this works behind the scenes. Let's see. In C++, the name of the array represents the location or address in memory of the first element in the array. That is, the element with index 0. When we access an array element using the subscript operator and provide an index in the square brackets, the compiler knows that you want the element that is at that offset from the beginning of the array. So all the compiler has to do is a pretty simple calculation. For example, if you want the element at index 2, all the compiler has to do is go 2 integers away from the beginning of the array, and there it is. Or 2 doubles, or 2 whatevers. The compiler uses the size of operator to determine where the element will be. This is one reason why raw arrays in C++ are so efficient. But remember, there is no bounds checking, so be careful. If you have an array of 5 integers and you ask the compiler for the integer at the 10th index, it will gladly do the calculation and give you whatever happens to be at that location. It's your responsibility to be sure that you're within the bounds of the array. Now let's head over to CodeLight and use what we learned and write some code with arrays. Okay, so now I'm in CodeLight and I'm in the Section 7 workspace and the arrays project. And here's my main CPP file. What I've done is I've created some examples where I'm declaring and initializing some arrays. I'm accessing array elements, I'm reading from them, storing values in them, and so forth. And that way we can go through this step by step so you can really understand what's going on. I've also commented a bunch of this out, and what I'll do is I'll uncomment as I go, and we'll build on this little by little. So the first thing we're doing here is I'm creating an array right here named vowels. That's the name of my array, vowels. And you'll notice that right in those square brackets, I'm not providing any information. So what I'm telling the compiler is, hey, you figure out how big this is based on the initializer. Okay, so in this case, I've got 5 characters that I'm initializing this to. So the array will be size 5. So what's going to happen is I'll have an array of 5 characters, and I'm initializing them to A, E, I, O, and U. Right? The name of this array is vowels, so I can treat it as such, and it's indexed from 0 to 4. Remember, there is no 5 here, so don't let that confuse you. Fine. Now, in this case, I'm saying the first vowel is, and I'm using an output statement, and I'm grabbing vowel sub 0. Well, that's this guy right there. That's the little a. So I expect this to print out the little a. In this case, I'm using vowel sub 4, which is the little u right here, the lowercase u. All right, so let's run this and see what we get. So what I'm going to do is I'm pressing Control F5 to build and run. And the output is the first vowel is A, and I'll move this over here so you can see. The first vowel is a lowercase a, the last vowel is a lowercase u, exactly what we expect. Okay. Now, what would happen, let me clear this real quick. What would happen if I tried to read from the console and I want to store whatever character I read into vowels sub 5? Recall, there is no vowels sub 5, right? It goes 0, 1, 2, 3, 4. What happens here really depends on a lot of things. Obviously, I'm going to read a character and store it in a location that's not part of the array, so there could be something important there, and I just blew it away. My program will likely crash, depending on what operating system you're on and what you're running. Your crash may look different from mine. So let me run this, and hopefully it'll crash. It may not. You never really know with this. Okay, there's first vowel is little a, second vowel is lowercase u. Now I'm going to read. So I'm going to type in, let's say, capital A. And when I press enter, that's my crash. Hopefully you can see that it says arrays.exe has stopped working. Close program. Depending on, again, what operating system you're working on, it may look different. But in this case, this is a good thing. My program crashed. I'm able to fix it. And obviously what happened here was, and I'll comment this out and I'll leave it commented out so it won't keep crashing. Oops, let me do that again. And I'll write something like, out of bounds. That way when you download in the example, you'll know what's going on. Right? I'll say, don't do this. Or be very careful with that. Okay, so that gives you an idea of what happens. It could be a pretty serious problem. And the real problem is that it may not happen every time. You may clobber some information that's just not even important. But you may clobber some information that's real important. Okay, so let's move on. In this example here, let me uncomment this code and I'll walk you through it. In this example here, I'm doing something very similar. I'm creating an array called high temps, and you can see that the name of the array is right there, high temps. Again, I'm not providing the size of the array because I'm letting the compiler figure it out based on my initializer list. There are 4 initializers. So I was going to create an array of 4 doubles, the first one being 90.1, the second one being 89.8, and so forth. Here I'm saying print out high temps sub 0, right? Remember, this would be 0, 1, 2, and 3. So in this case, this will print out 90.1. Now I'm saying high temp sub 0 is 100.7. So what I just did was I just changed the 90.1 to 100.7. This is an assignment statement. We're going to talk a lot about assignment statements in an upcoming section, but they're really, really straightforward when you see them like this. All it says is move this guy into that guy. Okay, so that's what we're doing, is we're just overriding that 98.1 to 100.7. And then when I display it, it's going to display 100.7 now. Okay, so what I expect here is the first time I output that guy, it's going to give me 90.1. Now I'm going to get 100.7. So let's try this out and see if that's exactly what we get. Let me build and run. The first high temperature is 90.1. The first high temperature is now 100.7. So here you can see some examples of declaring, initializing, and accessing array elements. Now here's another example here, and I'm going to comment this out as well. In this case right here, what I've done is I've asked the compiler again to give me an array of 5 integers and call it test scores. What's happening here is I'm getting an array of 5 integers, just like that. It's called test scores. Again, they're indexed from 0, 1, 2, 3, and 4. However, I never initialized them. So what you have in here is junk or garbage memory. Whatever happens to be in there, whatever bit pattern happens to be in there is still in there. So what this code right here is doing is it's displaying each one of those array elements. It's starting at the element at index 0 and going all the way through the element at index 4. This is what we'll do later on with looping. We can do all this in one statement with looping, and we'll learn how to do that a little bit later. Now, when I do this, I'm expecting junk. I have no idea what's in those cells, so I don't know what's going to print out. So let's try it and see. And you can see the junk right here, 4199136 and so forth. There's a 0 in there. The point is, you cannot rely on those values. You really don't know what's in there. Okay, so what do? Well, we can just put a couple of curly braces there in the initializer. That will initialize everything to 0. So if I run this again, I expect to see all zeros. I do. That's exactly what I want. Always initialize your arrays. Never assume that they've got any value in there until you put the value in yourself. I could also put a hard-coded 0 in there, and I'll have the same effect. But what if I do 100? This piece confuses beginning programmers sometimes. You may think that it's going to put 100 in all of those elements, but that's not the case. Let me run it and you'll see what happens. You see that? It put 100 in the first element and then the rest are zeroed out. That's the behavior when you put in less initializers than you have. So watch now, if I put a 90 here, then what's going to happen is it's going to set this element right here. It's going to set this element right here to 100, this element to 90, and then 0, 0, 0. Okay, so that's the behavior when you provide less than the size of the array as far as initializers are concerned. So again, I'll run this real quick. And what you'll see is 100, 90, 0, 0, 0. Let me clear this screen real quick. In this case, what I'm doing here is I'm reading integers from the console and storing them into those array elements from 0 to 4. So whatever was in here before is going to be removed now. So I'm going to initialize this to 100. Let's just go straight down by 10, 70, and 60. So 100, 90, 80, 70, 60 is how I'm initializing this to. I have a 5 here. I don't really need that 5 there. I could just get rid of it like that. I did it before so you can see how it initializes zeros. So I'll just get rid of that 5 right there. It's still going to create an array of 5 integers and initialize them to 100, 90, 80, 70, and 60. Now what I'm going to do is I'm just going to enter different numbers and then we'll display those new numbers right here with this code, which is the same code as we used before. Okay, so let's do that real quick. We'll build and run. So there's our original array, 100, 90, 80, 70, 60. So suppose I want to go now 10, 20, 30, 40, and 50. And I print them out. Now you can see that array sub 0 is 10, and the next one is 20, 30, 40, and 50. So you can see that those values are read from the console and stored in the array. The last thing we'll do is, this may give you a little bit of a different effect than you thought. Suppose that I want to output just the name of the array. Now you'll notice test scores right here. I'm not saying test scores sub 0 or test scores sub 1. I'm just saying test scores. Let's run this, and then I'll show you exactly what's going on when we come back. So I'm going to run this. And again, let's just enter those scores again. And notice what happens here. It says, notice what the value of the array name is. And you get some hexadecimal number. That number is actually the memory address or the storage location where the array is located. This is the way that C++ works with arrays. The name of the array is the location of the array. Now that's a strange number to write, so I'll just use 1,000 for it. That way we can make it a little bit easier to explain. So let's take a look at how this works. I've created that array, right? Test scores. And test scores is 5 integers, just like we saw before. Again, indexed 0, 1, 2, 3, and 4. This is called test scores. Now, when I say test scores, what's it going to do? Well, it's going to take the address of that variable. That variable is an address. So let's say that the address is 1,000. And then this address is 1,004, assuming that we have 4-byte integers. And this is 1,008, and this is 1,012, and so forth. What prints out here will be 1,000. And the calculation that C++ is doing that we mentioned in the slides. So for example, when I say test scores sub 1, as I'm saying here, what it's going to do is it's going to take test scores, which is 1,000, and it's going to add 1 integer to it, or in other words, go 1 integer away from it. An integer is 4 bytes. There you go. That's the address. That's the calculation it's doing. This is why when test scores sub 5 is referenced, it's going to do the calculation and come up with that number right there, and it's going to try to work with this guy. Well, this guy's not part of the array, right? The array ends here, but there's no real boundaries around the array. It's not like protected or anything. So in this case, something is going to change, and it may be a bad thing. You might crash your program. Okay, so hopefully this example helps you understand a little bit about the syntax of arrays, how to initialize them, how to use them, and a little bit more about how they're laid out in memory and some of the issues that you can have with them. In this video, we'll look at the syntax for multi-dimensional arrays in C++. We'll focus on 2-dimensional arrays, but you can use as many dimensions as are supported by your system. While there's no real limit to the number of dimensions you can have for arrays, be aware that some compilers do place limits on this, though the limits are quite high and you're unlikely to reach them. The syntax for declaring multi-dimensional arrays just involves adding another set of square brackets with the new dimension inside them. In this example, you can see we're declaring a 2-dimensional array named movie rating. This array has 3 rows and 4 columns, which means that the total size of the array is 12 integers. We have not initialized this array, so we should assume that the array elements contain garbage data until initialized. Let's see how we might model real-world data using this 2D array. Suppose we want to collect movie ratings. We have movie reviewers, and each reviews a series of movies with an integer rating from 0 to 5. We have 3 reviewers, and each has to review the same 4 movies. We could choose to model this data by having one array of movie ratings for each reviewer. So we could declare 3 arrays of 4 integers each and solve our problem like that. Another option is to use a 2-dimensional array. The first dimension, or row in our grid, is the reviewer, and there would be 4 columns in the grid, 1 for each movie. This is similar to the layout of a spreadsheet. In the figure, the reviewer is the first index or row of our array labeled in red, and the movie is the second index or column of our array labeled in green. Now it's pretty easy to go to a specific row and column and get or set that movie rating for that specific reviewer and that specific movie. Accessing the specific movie rating is easy. I can ask the user to enter a movie rating as an integer and store it in movie rating sub 1 sub 2. Suppose the user enters 5. This would update that specific element in the array. I can also display that element to the console using the same syntax. Initializing multi-dimensional arrays uses the same initializer list syntax that we saw with one-dimensional arrays. In this case, we provide in the initializer list the rows of columns. You could do this in a single line, but it's much more readable if you split it across lines as I've done here. You can see the initializer is providing 3 rows of 4 integers each, which is exactly how we declared the array. While 1- and 2-dimensional arrays are by far the most commonly used arrays in programming, extending the syntax to 3 dimensions and more is just as you would expect. Don't forget that the same characteristics hold for multi-dimensional arrays as for single-dimensional arrays. We'll see multi-dimensional arrays again when we talk about iteration in C++. So that's a look at C++ arrays. If you see them in existing code, you'll understand how they work, what they look like, and their syntax. Remember at the beginning of this section I mentioned that we rarely use C++ arrays in modern C++. Instead, we use vectors. Let's take a quick look at C++ vectors. In this video, we'll learn about C++ vectors. Suppose we want to store test scores for students in a class, but registration hasn't started yet, so I don't know how many students I'll have in class. Also, students drop and add as the semester progresses. How can I model this information using an array as we've seen to this point? Remember, C++ arrays are fixed in size, and I need to specify a size when I declare them. So what are my options? Well, I can always set the fixed size of the array to a size large enough so that it's unlikely I'll have more than that number of students. Many times this option is okay, but you'll probably make it too big and waste space. For example, we may have 30 students in the class, but we allocated 50 students in the array. Not only have I wasted storage space, but now I need to keep track of how many students are actually in the array. And of course, sooner or later, you'll get that one student that exceeds the size of the array. So what do? Well, we can use a dynamic array, such as a vector, to solve some of these problems. A C++ vector is part of the C++ standard template library. This is a library of powerful containers, algorithms, functions, and iterators. This means that we have available to us pre-written, pre-tested, easy-to-use components that we can use to help us solve our problems. We'll go over the main components of the standard template library toward the end of this course. We've talked about C++ being an object-oriented language. Well, when we create a C++ vector, we are creating a C++ object, and we can ask the object to perform operations for us. Vectors can grow and shrink in size at runtime, so it's a perfect choice to model my students. Vectors also provide syntax and semantics similar to arrays, so now that we've learned about arrays, understanding vectors will be pretty easy. In addition to the array-like syntax, we can also use lots of really powerful functions like sort, reverse, erase, find, and more. Vectors also give us the ability to use methods that provide bounds checking if we wish. Let's see how we can declare vectors. There are several ways to declare a vector. The syntax for declaring a vector changes slightly from that of declaring an array because vectors are objects. First, we must include the vector library. Also, the vector type is part of the standard library, so we must either use the namespace or use standard and the scope resolution operator. We can create a vector of any type we want, just like we did with arrays. Here's the syntax for vectors. Don't worry at this point what the differences are. We'll cover this in a future section. Since the vector is an object-oriented template class, we must include the type of the elements of the vector inside the angle brackets. So for example, vowels is a vector or a collection of characters. Test scores is a vector of integers. Both these examples create an empty vector that contains no elements. Let's look at a few other ways to declare vectors. In the first example, we declare vowels to be a vector containing 5 characters. In this case, I'm not providing an initializer list. We'll do that in the next slide. Instead, I'm using a constructor initialization syntax which provides information inside parentheses. This tells the compiler that you want 5 characters. In the second example, we declare a vector named test scores of 10 integers. Unlike arrays, these 10 integers will be automatically set to 0. I don't have to do that explicitly myself. We can also use initializer lists as we did with arrays to initialize vector elements. In this first example, we declare vowels to be a vector containing 5 characters. In the first example, we declare and initialize the vowels vector to the characters A, E, I, O, U. Note that there are single quotes around the character literals, not double quotes. In the second example, we declare and initialize a vector named test scores to the integers 100, 98, 89, 85, and 93. In the third example, notice that there are 2 values in the parentheses. The first value, or parameter, is the initial size of the vector, in this case 365. The second value is what you want to initialize all the 365 doubles to. In this case, we're declaring a vector of 365 doubles, and we're initializing all of those doubles to 80.0 degrees Fahrenheit. There are also many other ways to declare vectors. You can declare a vector to be a copy of an array or a copy of another vector. I think you're beginning to see how powerful vectors can be compared to arrays. So let's do a quick recap about vectors. We learned that vectors are an object-oriented container defined in the standard template library. We must include the vector include file to use them, and they belong to the standard namespace. Like arrays, vectors allow you to tell the compiler to give you a collection of as many elements as you want and give the entire collection a single name. Vectors are dynamic in size, which means they can grow and shrink as needed at runtime. Like arrays, vector data is stored contiguously in memory. Vector elements are individually accessible. Vector indexes start at 0 and end at position size -1. If you use the subscript operator, that's the square brackets, to access vector elements, then vectors will provide no bounds checking. This provides the same behavior as arrays. However, vectors provide a rich set of functions that do provide type checking. As a programmer, you can decide what you need to use. Unlike arrays, when you declare a vector, the vector elements will automatically be initialized to 0 unless you specify otherwise. So if you declare a vector of 10 integers, these integers will be initialized to 0. They won't contain garbage. Vectors are very efficient. And finally, we commonly use iteration or looping to process vectors just like we do in arrays. Later in this section, we'll talk about C++ vectors. In the next video, we'll look at how we can access individual vector elements, and we'll also see a few of those useful vector functions I mentioned. In this video, we'll look at the syntax for accessing individual vector elements. The first way to access vector elements is to use the array syntax we've already learned, using the subscript operator. That's the square brackets. We use the name of the vector followed by the square brackets with the index of the vector element we want inside the square brackets. For example, test score sub 1 refers to the element at index 1 in the test scores vector. In the code example at the bottom, you can see that the syntax is exactly as it was for arrays. Remember that vector subscripting or indexing is the same as in arrays. It starts at 0, so the first element of an array is at index 0. It's important to understand that when we use the subscript operator with a vector, no bounds checking will be done. You have to do it yourself, as with arrays. Now let's look at another way of accessing vector elements. We can also access vector elements using the @ method. This is the vector syntax. Since when we create a vector, we're really creating an object in object-oriented jargon, then we can ask objects to perform operations. These operations are called methods. The syntax is simple. The object name, in this case the name of the vector, followed by a dot called the dot operator, followed by the name of the operation we want performed. This is the method name. Don't worry about the jargon for now. It will come before you know it, and we'll cover it in depth when we talk about object-oriented programming. The C++ vector has a method or operation called at, A-T. So you can ask the vector to give you an element at a specific position, which you provide inside the parentheses. This style is actually much more intuitive since the name at provides context. So in the example, we've declared and initialized a vector named test scores to the 5 integers 100, 95, 99, 87, and 88. If we want to access a specific element, we use the at method and provide the element index. You can see that the syntax is very easy to read and understand. Test scores at 0 will refer to the first element in the vector. That's element at position 0. We can also use the same syntax when we want to modify vector elements. In this example, we're reading 5 integers from the console and storing these elements into the test scores vector. The last statement is an assignment statement, as we saw with arrays. We're storing 90 into the first element of the test scores vector. You're probably thinking, okay, that's pretty easy. Vectors are just as easy to use as arrays, but when do they change in size dynamically? The vector has a method called pushback that adds a new element to the end of the vector. Remember, all vector elements must be of the same type, so the element you add must be of the same type as all the other vector elements. In this example, we've created a vector called test scores that contains 3 integers, 100, 95, and 99. If this were an array and we wanted to add another test score, we'd be stuck since arrays are fixed in size. However, with vectors, we can use the pushback method and provide the integer you want to add within the parentheses. You can see that I'm asking the test scores vector to push back 80 and then 90. This will add 80 and then 90 to the end of the vector. Now the vector will contain 5 elements, 100, 95, 99, 80, and 90. How does this work? You don't have to worry about it. That's the beauty of vectors and of the other classes in the standard template library. The vector will take care of allocating or deallocating space, adding new values to that space, and so forth. You can concentrate on solving your problem. Okay, but what happens if you're using @ or some other vector method and you go out of bounds? Let's see. If you go out of bounds and you're using a method that does bounds checking, C++ will throw an exception. That's the jargon used to say that an exceptional condition has been encountered and the program can't continue. An error message is displayed and the program will terminate. This is a good thing. Now you have an error message that tells you what the problem was and you can fix it. The error message in this case is pretty long, but it's telling you exactly what happened. The error message may look different depending on the compiler you have, but the information provided will be the same. In this case, I bolded the important parts of the error message. You can see out of range, vector, range check, and the numbers 5 and 2. When you look back at your code, you'll see the vector has 2 elements and you want an element at index 5. You want your program to terminate or crash during testing so you can fix errors, but you don't want it to crash in production. This is where you can do exception handling. This involves catching these exceptions as the program runs and dealing with them so that the program doesn't crash. Exception handling is a more advanced topic, but I want to cover the basics, so there'll be a section at the end of the course just on exception handling. I hope you can see how much better vectors are than arrays and why you should use vectors in modern C++. Now let's head over to CodeLight and use what we learned and write some code with vectors. So now I'm in CodeLight, and let's do some examples with vectors. I'm in the 7-section workspace under the Vectors project. And here's my main file. Notice that I'm including the vector include file. You must do this in order to use vectors. Also, vectors belong to the standard namespace, so either you use the namespace standard or you'll have to do std, scope resolution operator, everywhere you use vectors. Let's talk about a couple of different ways to create vectors. In this first example here, I can create a vector called vowels, and it's a vector of characters, and that's the syntax. We put the type inside the angle brackets. Okay, so in this case, I've got vowels is a vector of characters, and this is an empty vector. Okay, it's of size 0. There's nothing in there right now. The only way to add things to it is to do something like pushback, which we'll do in a little bit. The second example creates a vector called vowels again. In this case, it's 5 characters long, and each one is initialized to 0. This third example here, which is the one I'm going to use in this example, I'm using an initializer list here, so I'm initializing the vector vowels, which is again is a vector of characters, to the characters A, E, I, O, U, which are my vowels. Again, remember that the character literals have single quotes around them, not double quotes. So at this point, I can simply output vowels sub 0 and vowels sub 4, which I expect to print out A and U respectively. Notice that even though I'm using a vector, I'm using the array syntax, so it's very, very familiar. Also remember that using the subscript notation does not do bounds checking. Okay, so let me run this. So there's my sample run, there's my lowercase a, my lowercase u, just what I expect. All right, so now let's take a look at another declaration of vector. In this first example here, I'm creating a vector called test scores, which is a vector of integers, and I'm creating a vector of 3 integers in this case. All of them will be initialized to 0. In the second example, I'm creating the test scores vector again. Obviously, I have to comment them out. You can't use the same name twice. That's why I'm doing this. It's a vector of integers, 3 of them. Each one is initialized to 100. And so those are 2 variants for constructing these vector objects. The one I'm going to use is this one right here, where I'm saying test scores, again, is a vector of integers, and I'm initializing them to 100, 98, and 89. So in this case, I'm going to get exactly 3 elements in my vector. My vector will be of size 3. Okay, so let's comment this out here. And in this case, I expect it to display 100, 98, and 89. Again, here I'm using the array syntax. So let me run this. And there you go, 100, 98, 89 using array syntax. Now we can also use vector syntax. So let me uncomment this. And now here you can see I'm saying test scores dot at 0. Test scores at 1, test scores at 2. So in this case, I'm using the at method to give me the value at that specific index. Same idea, except that this is a method and this will be bounds checked, which is very important to understand. Also, after I print out those 3 numbers, I'm saying there are so many scores in the vector. Okay, so what does that mean? Well, notice the size method here. This is a method in the vector class. So I can have my vector name, and I can just say something like dot size. It's that simple. And this will return however many items are in the vector right now. Right now, I have 3 of them. So I expect this to say there are 3 scores in the vector. Remember, the vector can grow and shrink dynamically. So it's important to be able to ask it, hey, how big are you? And that's what the size method does. So I'll run this one more time. And you can see here, my test score is using array syntax, 198, 89. Now my test score is using the vector syntax, 198, 89. We expect that because the vector hasn't changed. But here it says there are 3 scores in the vector. So here we're asking the vector, hey, how big are you? What's your size? And it's returning a 3. In this example here, what we're going to do is we're going to actually put some information into the vector. We're going to use the vector syntax from this point forward. So here, I'm saying enter 3 test scores, and then I'm grabbing 3 integers from the console, and I'm putting the first one at 0, the second one at 1, and the third one at 2. So I'm changing those vector elements. And then I just want to display them out again. So I'll uncomment this. Okay, so let's do that. I'll build and run again. Right now we've got 100, 98, and 89 in there. So let's just say I want 10, 20, and 30. And I want to display them out, and there you go. Updated test scores is 10, 20, and 30. So you can see that we've actually changed the contents of those vector elements. Now let's talk a little bit about the dynamic nature of vectors. This is the part that's really, really cool. I'm going to uncomment this bit out here. And notice the code here. It says enter a test score to add to the vector. Remember, the vector at this point has 3 elements in it. I need to read this into some variable, so I've created a simple variable right here called score to add. It's just an integer. This is not a vector. This is not an array. This is just a plain old integer variable. I'm initializing it to 0. That's the best practice. And I'm reading an integer from the keyboard, from the user, and putting it into score to add. Then what I'm going to do is I'm going to tell the test scores vector to push that integer at the back of the vector. So it's going to add it to the vector. If the vector needs to increase in size, it will. That's nothing we have to do. It handles that automatically. Then I'm going to say enter one more test score. So I'll read another test score from the console, and I'll push that score on. So at this point, when we display, we should have 5 integers now in the vector. I'm going to display them all at 0, 1, 2, 3, and 4. And then I'm going to say, hey, test scores, what's your size? And I expect a 5 here. Okay, so let's try that. All right, so I'm going to enter my test scores again. I'll say 10, 20, and 30. Now, remember, our vector contains 3 integers right now, 10, 20, and 30. So let's enter a test score to add. Let's add 100. And now it's saying, give me one more. Let's put in 105. Maybe I got some extra credit. Now when I press enter, I should expect to see 5 integers displayed as well as the size of the vector now being 5. So I'm going to press enter, and that's exactly what I see. The test scores are 10, 20, 30, 100, 105. Then it says there are now 5 scores in the vector. That's pretty cool. Let me show you an example of an exception. Right here, I'm saying this should cause an exception because I'm trying to access test scores at 10. If I tried to do something like this and just used array syntax, like that, no bounds checking will happen. I might just get a crash with no error message or anything. Instead, I'm actually saying at 10. And we could try to put a new line. It's not going to matter much because it's not going to do that because there is no 10th element. Let me run this again and I'll enter those numbers again. Okay, so again, we'll say 10, 20, 30. Let's push in 100 and 105. Now we should get an exception, and there's the exception. You can see the program is still stopping, but there's my exception. Terminate called after throwing an instance of out of range. There's a range checking problem, which is at 10, and this guy is 5 big. So that gives you a really, really good clue as to what's going on. All right, I'm going to comment that out so it won't affect us again. And then the last thing we'll do is I'll show you an example of using a two-dimensional vector. I'll uncomment all of this out. All right, so here, how do we declare a two-dimensional vector? Well, a two-dimensional vector is a vector of vectors. So it's a vector of vectors. And this is how I would declare a vector of vectors. I want to declare a vector that contains within it not ints, not floats, not doubles, but a vector. In this case, a vector of integers. And that's my movie ratings. I can initialize them right here. So going horizontally, that would be the first reviewer, the second reviewer, the third reviewer. And going vertically, this would be the first movie, the second movie, the third movie, and the fourth movie. Now, just like I showed you in the slides with arrays, I can use array syntax. So I could say here the movie ratings for reviewer number 1 using array syntax. And I would expect this to print out 1, 2, 3, 4. That's the first reviewer right up here. And in order to use vector syntax, we just use at, but we use it twice. Give me the rating at 0, that gives me this guy. And then once I have that guy, I can take at 0 for him, or at 1 in the next line, and so forth. So if I run this, I would expect to see 1, 2, 3, 4 both times. So let's run it. And we'll get by this part one more time. And there you go. Here are the movie ratings for reviewer number 1. Array syntax, 1, 2, 3, 4. Here are the movie ratings for reviewer number 2. That should have, sorry, number 1 again. That's right. Using vector syntax, 1, 2, 3, 4. Okay, so that basically covers the fundamentals of vectors, how to use them. There's so much more to vector, and we'll talk about all of that when we talk about the standard template library. But congratulations, you've just now created objects, used object methods, and we're on the way to object-oriented programming. Welcome to the Section 7 challenge. The purpose of this challenge is not to solve a specific problem, but to give you a chance to practice with vectors. We'll declare 2 vectors, and we'll add these vectors to a 2-dimensional vector that we'll declare as well. You'll get a chance to work with the vectors at, pushback, and size methods. And you'll also work with a 2-dimensional vector. Then at the end of this challenge, I'll ask you to modify a vector element and analyze the effect it has. You might be surprised by the result. Please go through the challenge in order and implement each of the directives in the challenge. Let's go over the details of this challenge together. First, I'd like you to declare 2 empty vectors of integers named vector1 and vector2 respectively. Then add 10 and 20 to vector1 dynamically using the pushback method. Display those 2 vector elements using the at method, as well as the size using the size method. Do the same thing for vector2, except we're going to add 100 and 200 this time. Then I want you to declare an empty 2-dimensional vector called vector2d. Remember, a 2-dimensional vector is a vector of vectors. Then I want you to add vector1 to vector2d using pushback. Then add vector2 to vector2d using pushback as well. Then display the elements in vector2d using the at method. Now comes the interesting part. I want you to change vector1's first element using the @0 method. And I want you to change it to 1,000. Then I want you to display the elements in the 2D vector again using the at method, just like you did before. and then finally display the elements in vector 1. Take a look at the results and see if it's what you expected, and see what you think happened. That's it. Good luck. Have fun. Once you finish the challenge, extend it in any way you wish. Remember, the more you practice, the easier programming becomes. Once you finish the challenge, join me in the next video and we'll go over my solution. Welcome back. I hope you enjoyed working with vectors and learned more about how to use them. You can find my solution in the Section 7 workspace in the Challenge Solution project. Let's go through my solution to this challenge one line at a time. I've inserted the challenge directives in my solution as comments, so it's easier to follow along. So, where do we start? First thing we need to do is we need to include the vector library. If you didn't do that, you probably got some syntax errors about vector not found and probably got a lot of errors. Also, we can use the namespace standard. We don't have to do this, but it makes the code a lot less cluttered and it's easier to display for teaching purposes that way. If you didn't include namespace standard, you might have gotten errors, and you probably did something like standard scope resolution operator vector. So let's do the first directive. It says declare two empty vectors of integers named vector1 and vector2 respectively. On lines 42 and 43, that's exactly what I'm doing. You can see vector1 is a vector of integers and vector2 is a vector of integers. There is no constructor here with the size. There's no initialization list, so these are going to be empty vectors. The second directive on line 45 says add 10 and 20 to vector1 dynamically using pushback. That's what I'm doing on lines 47 and 48. Vector1.pushback10, vector1.pushback20. These two elements will be added to the back of the vector and the storage will be allocated automatically for them. This is where we can see that the vectors can grow. On line 50, we want to display the elements in vector1 using the at method, and we also want to display the size of the vector using the size method. So you can see that between lines 52 and 55, that's what I'm doing here. On line 53, I'm simply saying give me the element at vector1's 0, and then give me the element at 1. So that will display 10 and 20 because that's what's in there. And then I'm going to say vector1 contains vector.size will return 2 because there's currently 2 elements in the vector1. So it should display vector1 contains 2 elements. Okay, so far pretty easy. Let me scroll up just a little bit. And on line 57, we're doing the same thing with 100 and 200 but to vector2. So I'm adding 100 and 200 dynamically using pushback on vector2. Vector2 was empty, so after this, vector2 should have 100 and 200 and a size of 2. What we're doing on lines 64 through 67 is the same thing we did with vector1, except we're doing it with vector2. We're displaying the results. This should display 100, 200, and vector2 contains 2 elements. Okay, let me scroll up a little bit more. Now on line 69, the directive says declare an empty two-dimensional vector called vector2d. And there's a little hint there that says remember that a 2D vector is a vector of vectors. So this is how we would declare this. Vector2d, that's my object, is a vector of integer vectors, or a vector of integers, however you want to pronounce it. So you get the idea there. So it's a vector that can hold other vectors. Therefore, you have the two-dimensionality. On lines 74 and 75, what we're doing is we're adding an entire vector to the vector2d with pushback. We can do that, right? Because it's a vector of vectors, so I could certainly add a vector to it. And that's what's happening on lines 77 and 78. On line 77, I'm adding vector1 to vector2d using pushback, which means that, remember, vector2d at this point was empty. So storage will be allocated, vector1 will be put in there. Doing the same with vector2. So at this point, we'll have a two-dimensional vector that contains 2 vectors. So on line 80, we're displaying the elements in vector2d using the at method. So you can see here I'm displaying the element at 0, 0, and then the element at 0, 1, and then the element at 1, 0, and the element at 1, 1. So this should display 10, 20, and 100, 200. So this is the interesting part now. I've asked you to change vector1's first element, right? The element at index 0 to 1000, and then display the vector again. What did you expect? Some of you might have thought that that first element would have changed, right? Because after all, we did put vector1 into the 2D vector. And you might be surprised that it didn't. And we'll talk about that in a second. But here we're displaying vector 1 just to see if it actually did change. So let's run this and we'll walk through the output. So I'm going to build and run. And you can see at the beginning we're saying, okay, vector 1, right, we pushed the 10 and the 20, so that was fine. And then vector 1 contains the 2 elements. That's what we expect. Vector 2, we inserted the 100 and the 200, and vector 2 now contains 2 elements. Vector 2D contains vector 1 and vector 2 within it, right? Again, it's a 2D vector. So the first one was 1020, the second one was 100, 200. Pretty cool. But now at this point, what we did was, this is where we're at right now. We just changed vector 1's first element to 1000, and then we printed out that 2D vector again. But you can see the 2D vector, there's no 1000 here where the 10 is. That's where you would expect it, right? There isn't. The reason for that is that when you add elements to vectors, you actually make a copy of what you're inserting. So that tells you a little bit about what's going on. A little bit later on in the course, what we'll do is we'll have vectors of references or vectors of pointers, and those are a little bit different because here we can actually change what it's pointing to and it'll be reflected in the vector. But when you're using integers and floats and doubles, remember, we're making copies of what we're putting into the vector. All right, so that completes this solution. I hope you enjoyed the challenge, and I'll see you in the next video.